Hello, everyone. Thank you so much for joining me today. My name is Shannon Holmes. I'm a medical physicist with Standard Imaging, and today it's my distinct pleasure to be able to talk with you about our scintillation detectors and how you can make measurements without perturbing the beam. Let's see if my slides will change. There we go. At Standard Imaging, we think that it's your time, be precise, and of course we are here to support you with that. A little housekeeping before I really get into the meat of the talk. I am recording the webinar today, so if for some reason you have to step out in the middle or you want to share it with a colleague, watch your email probably this afternoon or tomorrow for a link to the recording. If you have questions as I'm going through the presentation today, please feel free to enter them at any time into the question portion of the GoToMeeting dialog box. I will try and answer those as they come up, but of course, if I miss any, I'll try and circle back around to those at the end of the talk as well. If you're not so familiar with Standard Imaging, we are in Middleton, Wisconsin, just outside the state capital of Madison. We've been in business since 1989, and from those modest beginnings, we have grown to design and manufacture a full suite of QA products for radiation therapy. So if there's a solution that you are looking for, please contact us. We have an answer for you. So why scintillators? That's usually the question I get asked first. We're very used to ion chambers and diodes. Why do we need to add another different type of detector to our arsenal? And really the advantage here, as the title of the talk indicated, is the water equivalence. So these are organic scintillating materials, or it is an organic scintillating material that's water equivalent for both MV photons and electrons. So the key here is that you're not disturbing that dose distribution and right at the point where you're trying to measure the dose distribution. They can be made very small. They don't show dose or dose rate dependencies or energy dependencies. And the beam quality correction factor is unity, again, because of that water equivalence. There is a minimal temperature dependence with these. If you were to calibrate them at room temperature and then use them, say, at body temperature, we are not cleared yet for on-patient measurements, but somewhere down the road, if we do get cleared for that, there may be a correction that needs to be applied if you're characterizing it at room temperature and measuring at a higher temperature. But if all you're doing is QA measurements all at room temperature, you can usually ignore any temperature dependence. The other advantage of these is that there's no ferrous materials at all in that fiber, and so they can be used with MR-Linacs. I'm happy to report that we've just recently released a standard package for this W2 setup that includes a fiber that's long enough to keep the electrometer outside the 5 Gauss line, so that it's much easier for you to use it with the MR-Linac. You have the cable slack that you need for the various configurations that you might want to measure in. So how does our scintillator work? I mentioned it's an organic scintillating material. The first generation device was a 1 millimeter diameter, 3 millimeter long active scintillation region. That's the W1. With the W2, we have been able to go offer both a 1x1 scintillator and a 1x3 to match the prior version. It also gives a little bit of an advantage in terms of the slightly larger small fields get a little bit better signal to noise just because of the 3 times the higher signal that you get from the larger scintillator. One of my colleagues likes to call the fly in the ointment is that for scintillation detectors, you do have to correct for Cherenkov light. So this is essentially a stem effect in these detectors. It's additional light that is generated in this optical transfer fiber by the high energy electrons that are traveling through that fiber. We have implemented a 2-channel chromatic correction based on a publication from Matthew Guyot et al. In Med Physics from 2011, showing that the varying lengths of the fiber although they generate different amounts of Cherenkov, the spectrum is stable, and so you can, if you split the spectrum into 2 portions, you can use the amount of Cherenkov in the one portion of the spectrum to subtract the Cherenkov from the signal portion of the spectrum. And I guess I have a slide for that later. We'll get into that. The other thing about the scintillators that is not quite ideal, but is quite workable, is that they're not absolute dosimeters. They're not the sort of thing that you would send to a calibration lab. They'd get their dose calibration, and you would expect that to be perfectly stable for the next 2 years before you send it back again. Because this is a plastic that is being irradiated, plastics degrade under radiation. The signal decreases as it gets dose. So you can tie the output to dose through giving it a reference dose and knowing then that correlation between the dose that was given and the amount of light that's generated. But you do have to recalibrate it periodically as the material accumulates dose. So this is, I guess, a little bit better pictorial description of that two-channel chromatic correction. We have a blue scintillator, so it produces a spectrum a little bit like this. Cherenkov is a broad spectrum contaminant across the field, and so the composite is, of course, this thicker dark line, what is measured by the full system. However, if we split this into the blue section of the spectrum and the green section of the spectrum, and we have you do two sets of measurements, one that we call a minimum fiber configuration, where this is the cal slab for the W1. You would have the fiber coming straight out of the field. This is a water tank jig for the W2, where again you would have the fiber coming straight out of the field. That's what we would call the minimum fiber configuration. Keeping the dose to the tip of the fiber the same, and changing the amount of fiber in the field. So this we call the maximum fiber configuration, where it's wrapped around in this jig or here in the cal slab. You can get a change in the Cherenkov spectrum without changing this dose spectrum that comes from the scintillator at the end of the fiber. We then use the change in the signal in the blue channel compared to the green channel to create what's called a Cherenkov light ratio. And then this factor is a constant. And it's used in subsequent measurements to take the signal in the green channel multiplied by that CLR to subtract that Cherenkov contribution that's in the blue channel. And that gives you your actual scintillation signal. And it's quite stable and robust method to do it this way. We've had good luck with it. So if you do a dose calibration, this becomes just a gain factor or a unit conversion factor that's multiplied by that scintillation signal to go from the current that was, or the charge that was measured through the electrometer to dose, because that's a fixed ratio as well. So you would give it dose here, it's a 10 by 10 field size that's marked out. You give it a known dose in reference conditions. You could do the same in the blue jig here or in the scanning configuration to give it a known dose and to create that conversion. So the W1 was our first generation. It's still available and it's quite widely used, has been available since 2014. It is, as I mentioned, that 1 by 3 millimeter active area. There are a fair number of publications on it just because it was a novel detector, particularly at the time, although there's still not much for competition. It's quite good. But the one that I have been citing the most lately is the joint publication from the AAPM and the IAEA on small field dosimetry. So that's TRS 483, which lists some tables of field output correction factors for specific energies as a function of field size. They leave out data when there was too high an uncertainty or the detector was not deemed appropriate due to that uncertainty or variation in the measurements for the small fields. But field size specific beam quality correction factors for specific energies. And in every table that the scintillator is included in, you get a row of ones, which makes this correction so much simpler for you. And that this actually has provided a lot of confidence for centers that have been really hesitant to get into the very small field or the world of very small fields because they weren't confident that they were applying some of these other corrections properly. So this water equivalence has been a very huge advantage of the scintillator over some other detectors. Even the diamond detector, which claims water equivalence, does require some of those corrections at the small fields. So it is the limitations of the W1. It is just a single point measurement system. It was the first generation device. It was designed just for output factor style measurements, right in the middle of the field where you have a reasonable amount of signal. It also is it is permanently affixed. I guess not permanently, we can replace the fiber, but it's not user replaceable. The fiber is attached to the optical detection system. So the fiber and the photodiodes essentially are one unit, and out of that we've split it into blue and green channels, but you need a 2-channel electrometer in order to read those 2 channels separately, perform the Cherenkov subtraction properly, and give you the proper result. So our Supermax electrometer has routines built into it for you to be able to characterize your scintillator, your W1, save the CLR values and dose calibration values so that any subsequent measurements, it can automatically apply all of these. You could certainly use a different 2-channel electrometer, but it's a lot more legwork on your end because you have to do all of the calculations in a spreadsheet yourself. So with the W2, this is the 2nd generation device. This was designed so that you could use it with a scanning tank. We were also able to improve the sensitivity of the optics and decrease the noise floor that comes with the electronics for processing the signal by making one dedicated electrometer that takes in that optical signal. It's now user replaceable fiber, so you can use either the 1x1 or the 1x3, or if your resident rolls a cart over top of one and kinks the fiber and you need a new one, all you do is get a new fiber and you plug it into the back of the device. Because we've integrated all of that together, we were able to go down to allowing the 1x1 millimeter scintillator. There's a question, does the W2 and the blue CalJig fit in the universal detector holder for the Sun Nuclear 3D tank? Yes, the W2 does. I'm not sure if the universal holder on the Sun tank will hold a vertical plug or a stem like for a scanning diode, but there is a workaround for that as well. There is a rectangular field method you can use for the CLR characterization where you have it in the scanning orientation and just use something like, say, a 2x20 field, and you have it coming in from the side of the long skinny field for the minimum fiber configuration, rotate your collimator to get the maximum fiber configuration, and you can do that just in the scanning orientation if you don't have a vertical like a diode holder for your Sun 3D tank. Good question though. The Max SD basically acts as a pass-through then. I should start with, it works fine as a standalone. It is designed so that you can do your characterization measurements for your CLR, you can do your dose calibration, it will store those values just fine. You can do point measurements with the system directly. We have a web page interface, you can run it from outside the room, you can zero it, you can collect all your measurements and then export it as a CSV if you want, or copy it into your Excel spreadsheet to have all your data available right there on the screen in front of you. So it works just fine as a standalone for those point measurements. If you'd like to scan with it, you want to collect the data on your water tank scanning system. You want that electrometer to register the signal from the scintillator, but of course it doesn't take in an optical signal. It doesn't have the smarts or the programming to be able to do the 2-channel correction. So the Max SD acts as a pass-through where it takes in that optical signal, does a fast Cherenkov correction, and then converts that corrected signal into an analog output that can be sent to your water tank for scanning those small fields. So it does every 10 milliseconds, it does an integration and sends the signal over to your water tank. So you do have to scan slowly with it because it's a low signal device, but because you're doing just small fields, it's totally worth it. So this is that configuration I was saying you could use with the other water tank. It has a sleeve adapter or stem adapter that basically increases the diameter of the fiber stem so that it can be held in any standard chamber holder for whichever tank you're using. This, of course, is our Dose View 3D tank. It will fit any scanning chamber holder that will hold either a 7mm or 8mm diameter chamber or chamber stem. So if you're scanning with it, you would do those CLR measurements beforehand, just with the Max SD or just before scanning. It could be all set up, it doesn't matter. Then you hook the triax output from the max SD to the input channel on your scanning tank electrometer. And from the scanning tank perspective, it really just looks like a diode. You're not applying bias to it, but as soon as there's radiation, there's a current, a signal that arrives at the water tank. And then this is that view down into the tank. Again, that does have a vertical post that would be held more in the diode scanning configuration for minimum and maximum fiber. There's another question I see, is there a holder for the PTW beam scan tank? As long as your tank will accept that, I think PTW is the 7mm diameter, yes. So it's really just this acrylic sleeve, has a wider end and a narrower end. There's a thumb screw, I think you can see a little bit here. There's a thumb screw on it that you would gently clamp down on the fiber. The end of the fiber has a Kapton tube around the outside of it, so it's a little bit stiffer just at the end. And then you can clamp down on this acrylic adapter without worrying about either crushing your fiber or having to clamp down on a really, really tiny fiber in a holder that's meant for a bigger chamber. It also allows you to get the tip of the fiber out away from the scanning apparatus, so there's no concern about the side scatter or back scatter from any of that as well. Little bit of examples here of what people have done with the W2. This was the initial publication that came out from NYU Langone, just comparing the W2 with radiochromic film for scanning. So this is a 1 centimeter field, comparing the W2 scan with the film measurement. And also looking at some of the other characterization components of the fiber, just to make sure that nothing had changed from the W1. It's the same fiber, honestly, so we didn't expect any change. None of the construction was different. The only thing that's different on the fiber construction is that for the 1x1, it's a shorter section of scintillator. But they did look at dose rate and dose dependence as well. And then Richard Popple's group at the University of Alabama at Birmingham was looking at baryon hyperarc measurements, I believe, where they looked at patient targets, how small a patient target or treatment target they could manage and accurately measure, again, compared with radiochromic film. And they looked at targets all the way down to 3mm diameter and got excellent agreement between their film measurements and their scintillator measurements. This image on the right, this is the chamber plug that they were using. They have a phantom that's a little similar to our SDVP phantom, which has a water equivalent plug that you can use either in water equivalent material or in a lung material. So it kind of simulates that lung tumor. But if you look at the W2 is water equivalent, so it's hard to pick it out in the scan with the W2. So they do come with localization fiber markers. So it's just a dummy fiber with a BB at the end of it, so that when you're doing your planning or when you're doing your alignment for these measurements, you have something you can actually see to draw a target on or to align to. So that's what I had. Please, if you want more information, please visit our website, contact your sales representative, contact me. I guess I didn't put my email up there. It's sholmes@standardimaging.com. But we'd love to talk to you about it. Ideas you have, questions you have. It's the more the merrier. I love those sorts of interactions. So if you have questions now, I'm happy to stick around and answer them. Otherwise, thank you so much for your time today. I know we're all busy. I appreciate that you've set aside some time to come listen to this today, to join me, and I'm happy to answer any questions you might have. There's a question about how accurate the system is, and I did not give a number for accuracy. Goodness, I'm not sure. I've been asked that question to be able to give a specific answer. There have been some investigations. I think there are actually a couple of publications or abstracts that were accepted for posters or e-posters at AAPM this year, looking at the accuracy of measurements compared with other detectors or compared with film. and it's usually on the order of 1% that those discrepancies show up. So it is a highly accurate system. Actually, I should say it's usually less than 1%. And the W1 is kind of fun to have watched the progression on this. The W1 has gradually become, instead of the detector that people are investigating in order to see how accurate it is, it's become, and now the W2 has become the standard to which everything else is being compared. And so it is a very highly accurate system when it's used properly. Well, thanks so much again, everyone. I do appreciate your time and questions. Oh, one more question. What application do you plan to use it for? Small field characterization, potentially for really doing serious end-to-end testing of your system to make sure with, an SRS phantom like our Lucy phantom or the stereotactic dose verification phantom, we call it the SDVP, that has those lung slabs as an option. It's really for building that confidence that you can, the doses from those extremely small fields. You can treat accurately with those extremely small fields, so that you have the confidence when it comes to time to treat patients with that. Is it possible to use it with BT? You mean Bluetooth? It does not have Bluetooth. It does just have a fixed Ethernet connection at the moment. Oh, brachytherapy. Yes, so there are some investigations of using it with brachytherapy. It's not something that we have characterized. That's more of a research use at the moment. So there are a few differences with brachy that need to be investigated. It's not quite as straightforward as external beam, but it would certainly be of research interest to us if you want to reach out. Well, thanks so much, everyone, for attending. We look forward to seeing you on more standard imaging webinars in the future. And of course, feel free to follow up with us via email or through the website if you do have additional questions. Thanks so much.